Okay, let's talk about the mole. So, Avogadro. Talking about an Italian here, dead white guy number 5, I think. 7, 10, I don't know, I lost count. Amadeo Carlo Avogadro, Count of Caragna and Cerreto. He also played with gas. That was a way to get famous in around 1800. He realized that there was a way to measure the mass of Dalton's atoms by measuring the pressure, temperature, and density of a gas. We'll talk more about Avogadro's work in Chapter 9. Okay? But for now, just realize that this was a huge deal. That he had found a way to measure the mass of individual atoms by working with masses of gases, actually pressure, temperature, and density of a gas. Okay, it was huge. It was a really big step forward. Okay, oh God, 5 internet points for anyone who recognizes this cool cat. All right, so based on that, we have the concept of the mole. Okay? One atom of hydrogen has an atomic mass of 1.00784 atomic mass units on average. One atom of oxygen, 15.99903 atomic mass units. One molecule of water is 2 atoms of hydrogen and 1 atom of oxygen. If we want to look at actual chemistry, then we need a way to measure atoms. Because, 2 atoms of hydrogen plus 1 atom of oxygen makes 1 molecule of water. 15.999 atomic mass units of oxygen plus 2.015 atomic mass units of hydrogen makes 18.014 atomic mass units of water. Okay, so mass is very different from the number of atoms. That's why we have the mole. Mass is the measure of the amount of matter. The mole is the measure of the amount of things. That's kind of weird. But the mole measures the number of things. But we're talking about when you have quantities that are too large for you to count. Okay? You can't count individual atoms because there's just skajillions of them. Not even billions, not even billions of billions, but billions of billions of billions. Okay, it's just a ridiculously large number of atoms. We can't count how many there are, but we can measure how many there are, and that's what we use the mole for. The mole measures the number of things. So the mole is for when counting does not work. And for that, we use Avogadro's number. That's this thing right here. It's named for Avogadro. 1 mole is 6.022 times 10 to the 23rd of a thing. It's a very large number of things. And scientists, when they get bored, they occasionally like to come up with real-life visualizations of the number of items in a mole. So, for example, what we're looking at, 60222, it's just a very large number. But 1 mole of pennies is 6.022 sextillion dollars. That would be enough to buy the solar system, I think. It's an absurd amount of money. Hundreds, thousands, millions, billions, trillions. So that is $6 billion trillion. Wait, hundreds, thousands. 6 million trillion, sorry, dollars. All right. 1 mole of popcorn would cover the U.S., the continental U.S., to a depth of 9 miles. A mole of puppies would undergo gravitational collapse into a very sad mess of puppies, a sphere of no longer living puppies. Moles are big because atoms are tiny. So the way they count the mole is based on a useful measurement. So by definition, they defined the atomic mass unit by reference to carbon-12. Okay, carbon-12 has 6 protons and 6 neutrons. And they defined that as having an atomic mass of exactly 12 atomic mass units. And also by definition, 1 mole of carbon-12 has a mass of exactly 12 grams. So the definition is 1 mole of a substance has a mass in grams equal to the mass in atomic mass units of 1 particle of the substance. So one particle of carbon-12, one atom of carbon-12 is 12 atomic mass units. Therefore, 1 mole of carbon-12 is 12 grams. And they did the counting and so on, and they found that it takes 6.022 times 10 to the 23rd particles of a substance to do that. For any substance, every substance, all substances, doesn't matter what you're talking about, 6.022 times 10 to the 23rd particles of that substance will give you 1 mole. And that will have a mass in grams equal to the atomic mass of one particle of that substance. Okay. So that is why I had the term molar mass back in section 5. Molar mass is sort of equivalent to the formula mass or molecular mass. Okay? So it's the mass of 1 mole of a substance. So carbon has an atomic mass of 12 point, or sorry, atomic mass. It's a molar mass of 12.011 grams per mole, because we're not talking about carbon-12, we're just talking about general carbon, and that's the number, again, right off the periodic table. So 12.011 grams per mole. That means that 1 mole of carbon has a mass of 12.011 grams, just as 1 atom of carbon, on average, is 12.011 atomic mass units. Okay. Oxygen is 31.998 grams per mole. Be very, very careful. Okay, I didn't say an atom of oxygen, I just said oxygen. And if you're not careful, you'll get tripped up on that, and you might go a little bit sideways. Okay, so let me bring this up. Because oxygen is one of the diatomic elements. Okay. Atomic, diatomic, 2 atoms. Okay. There are a number of elements that in their native elemental state are composed of 2 atoms. Okay. So remember that with Brinkelhoff. These are the elements that exist as in their native elemental state. They are not individual atoms, they are molecules, and each molecule is 2 atoms of that element. Okay. So if we don't specify atoms, if we don't specify that it's part of a different molecule, if you see one of these elements, remember that it is a pair of atoms. And that's why when you talk about oxygen generally, it has a molar mass of 31.998 grams per mole. Because 15.999 plus 15.999 is 31.998. Carbon dioxide is 1 atom of carbon plus 2 atoms of oxygen. Thus, it is 44.009 grams per mole. So if you have 1 mole of carbon dioxide, you have 44.009 grams of carbon dioxide. So that's why that's half the reason we use the mole, because 12 grams of carbon, it's a small handful of carbon. 31.998 grams of oxygen, that's actually, because oxygen is a gas, it's a significant quantity. It's a large amount of oxygen. Likewise, 44.009 grams of carbon dioxide would be about 25 liters. 12 2-liter bottles of carbon dioxide. Just of carbon dioxide, not of soda, just of carbon dioxide. All right. So these are, but the thing is 12, 32, 44 grams, these are realistic quantities. They are quantities that we can actually work with in the lab. You can't work with individual atoms. So all roads lead to mole. This is a chart we'll expand on moving into the future. But particles, okay, whether we're talking atoms or molecules or formula units, particles are the things that actually interact with one another in the lab. Mass is the stuff we can measure and work with in the lab, and the mole is the link between them. Okay. So you use the formula mass or molar mass to convert from mass to moles. You use Avogadro's number to convert from moles to particles. Okay? So the formula mass or molar mass, you get that off the periodic table. Remember, you add up the masses of all the individual atoms. Avogadro's number is just 6.022 times 10 to the 23rd. I'm going to go ahead and write that out again so that you remember it. This is important. I don't think they'll give it to you on the test. It's something you have to remember. 6.022 times 10 to the 23rd per mole. Okay. We leave blank up top because it could be atoms per mole, it could be molecules per mole, it could be anything per mole. Okay. So. The other half of the reason we use moles is because it relates to reactions and so on in exactly the same way that atoms do. Okay? So when you look at the reaction of hydrogen and oxygen to make water, 2 molecules of hydrogen will react with 1 molecule of oxygen. Remember, they're both diatomic elements, Brinkelhoff. To react, the 2 molecules of hydrogen plus 1 molecule of oxygen makes 2 molecules of water. In the exact same way, moles will react. So 2 moles of hydrogen will react with 1 mole of oxygen to make 2 moles of water. So moles have the same sorts of ratios as molecules or atoms, but in real laboratory significant quantities. So those are why we use moles, because it's real quantities that have the same sort of ratios as atoms or molecules. Okay, by contrast, if you look at this would be something like 2 grams of hydrogen plus 16 grams of oxygen to make 18 grams of water. Nowhere near the same sort of ratio. Mass does not have that ratio. Moles and molecules, or moles and atoms, moles and formula units, whatever you're talking about. Moles have the same ratio as the individual atomic or molecular particles. Mass does not. That's why we have to work with moles. You are going to be converting into and out of moles all the damn time in this class. Get very, very good at it. Hint, hint, hint. So, here is a table or chart. I'm not going to play a funny song this time. Just go ahead and work on this on your own, rather than me trying to go through the whole darn thing. I will show you in class. I will work through this example, but I want you beforehand to have at least tried. FM means formula mass, or molecular mass, molar mass. It's sort of the general, most universal sort of catch-all term. Then the actual mass would be the thing you put on the balance that you measure in the laboratory. Moles is, the number of moles of that mass, and then particles is the number of particles of that particular thing. So this is this leftmost column is it's like, instead of the atomic mass, it's the molar mass or molecular mass of the substance on the left. But then the other 3 columns are for some particular sample of that thing, rather than just the general. So this is general. The formula mass of all propane will be 36, about 45. But a particular sample of propane could have a mass of 28 grams, or a mass of 5 grams, or a mass of 200 grams. This particular one is 28.12 grams. Okay. Then the formula mass of hydronium is going to be about the 19. But this particular sample is 1.8740 moles of hydronium, and so on. Okay. All right. So all right. So practice, 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 practice. You absolutely have to practice this. You need to be good at going back and forth between moles and mass and between moles and particles. They will absolutely expect you to be able to go between moles and mass and moles and particles on the test. And if you can't go between moles and mass, all just sort of easily, quickly, you will not do well in this class. It is absolutely vital. This is never going to not be important in chemistry. You absolutely must be able to go between moles and mass using the molar mass of the substance. and that's a mole. He is a very fuzzy, happy-looking guy. He aerates the soil and occasionally eats root crops. I believe they also eat bugs. The moles have very big paws. They are very good at digging. He doesn't look so happy. Yeah, there's a mole. He's a funny-looking guy. He's a cute little guy. All right, and that does it for the mole. Go ahead, practice, 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 and I will see you again